Hello, my name is Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Welcome back, folks. We're going to do our studies this an episode on the Section 5 of TEMA, Mechanical Standards. In particular, we will reference the 10th edition and we'll make some allusions to some earlier editions because over time the TEMA editions have changed. So let's take a look at the overall architecture of TEMA. We began with section 1, which is essentially the nomenclature, definitions and terms. And we have section 2, which is the fabrication tolerances. 3 is the fabrication and performance. 4 is the installation, operation, and maintenance. And 5 is, which is what we're focusing on, will be mechanical standards. And 6 is an interesting section called flow induced vibration. 7 is thermal relations. And 9 is the physical properties. And W is general information. And there's actually quite a lot of good stuff in part W or section 9 to have a look at. And section 10 is called good practices. And then there's an appendix A for tube sheets. Let's take a look at the outline for this video presentation. We're going to talk about the limits of applicability as found in section 5, the TEMA Exchanger classes. We're going to talk about the construction codes, materials of construction. And then once we're ready, we're going to dive into the comparison of TEMA Class R, C, and B designs. In particular, we'll bore down, we'll look at the selection of TEMA classes. We'll look at the corrosion allowance, how it varies from R to C to B. Look at the tube pitch. We'll look at the longitudinal baffle thickness. Look at the tie rod size and numbers. We'll look at the floating heads. So let's begin. Start from the top here. The applicability of the use of TEMA tubular exchangers. This is a reference to the 8th edition and later. Right at this making of this video, we were at the 10th edition. So what it said was this specification is applicable for 100 inches or less in diameter, inside diameter, and if the product must of the shell diameter and the design pressure must be equal to or less than 100 ksi. They also say that it's applicable only if the pressure is not greater than 3000 psig design pressure. They say the maximum shell pressure must be less than 3 inches. And the stud diameter must be less than 4 inches. Something to be aware of is that the earlier editions had different requirements. So it's important if you're working on a unit that's older that you consider these limitations. So in the 7th edition, for example, which was 1988, TEMA limited exchanger size to 60 inches. In addition, this hasn't changed. The product of the shell diameter design pressure must be equal to or less than 100 ksi. And we need to not exceed 3000 psig. And in this case, the maximum shell diameter is limited to 2 inches. And the last one is the stud diameter can't be greater than 3 inches. TEMA exchangers are divided into 3 different classes or groups, and the construction will vary with the different levels. There's a type R, C, and a B, which is shown here, the TEMA Class R, which is R for refinery, and then C class and B. So in order of highest cost is R and progressively lower down to B. But in terms of reliability, you trade cost for reliability. R is the most reliable of those components. So we're going to spend time today in this video to compare the different classes. So it's easy to see the differences when, say, for example, one wants to go from a Class B exchanger, replacing it with a Class R, or vice versa. There's some information that might be useful. It has to do with the construction codes, and this is more about definitions. Important to get this behind us. So TEMA is based upon ASME Section 8 Division 1, and throughout this document it'll be referred to as the code. It doesn't mention anything about Division 2 or Division 3. It's Division 1. So just be aware of that. And if you want to know the differences between the different codes, the divisions, I have a video that you can look up in our library, and it can talk about the differences. Okay, the next one, when we are referring to specific sections of the code, we refer to those specific sections as ASME. It has to do with materials. And let's talk about the definitions. So they refer to carbon steel into the TEMA specification. And when they refer to carbon steel, they mean part UCS of Section 8 Division 1 for what carbon steel means. And they have a list of very specific ASME codes that are used for the materials. Now, metals that are not part of UCS, except for cast iron, and there's specific requirements for that, are referred to as alloys. So you got carbon steel group and then alloys. Part 1.1 in section 5, it's the section called applications, and this is where we look at the applications of TEMA R, C, and B. So TEMA R is for severe environments, and particularly we use that in the petroleum industry, where there's a focus on higher reliability. The second one is called commercial service, C, moderate service, and the third one is light service, chemical process service. And basically, when you look at these, R again is the most reliable, and B is the least reliable. But it's in different services you may not need that reliability. The most important thing is it's based upon cost. So a chart you would pay more money for a Class R, and it's something to consider when selecting this kind of equipment. Part 1.5, Corrosion Allowance, CA for carbon steel, we'll look at that. So for Class R, it's 1/8 of an inch. For Class C, it's 1/16 of an inch. And for B, it's the same as Class C. Now there's a couple notes here. Alloy parts do not require corrosion allowances. And Class R, for which cast iron fits in, would have a corrosion allowance of 1/8 of an inch. And for Class C and B, you would use 1/16 of an inch. 4 has to do with the 2-pitch and minimum clean lane. The 2-pitch is 1.25 times the OD and a 1/4 inch for the lane. So what is a lane? Well, it's that distance between the ODs of the pipe. So you can, if you can see my little cursor, it's there and here and here. And this is an example of a triangular pitch. So one thing to realize is that just because Class R has a 1/4 inch lane, it's only when required by the purchaser, and the default would be a 1/4 of an inch for that lane. And for Class C, it's a similar formula for the pitch, which is the distance between these two tubes would be 1 1/4 times the OD. And so another rule is if it's greater or less than 5/8 of an inch OD, and it's an expanded joint, then you can get down to 1.2 times OD, so you get a little bit tighter. And that can really help with your heat transfer because you can get more heat transfer area in a smaller space. Similarly, we still have the same formula for the pitch for Class B, but the shell diameter in the lane is really required by purchasers. So there's a little bit more freedom in specifying that. But basically the defaults are by TEMA, as if you're basically less than 12 inches, you can use 3/16 inch lane, and greater than that, a 1/4 inch lane. Okay, let's look at 4.4.2 longitudinal baffle thickness. Quite a few rules about this one, and tried our best to simplify them. The first rule is if you're going to be using leaf seals, T must be at least greater than a quarter, equal to or greater than a 1/4 of an inch for welded in. The same rule applies, but you can also have the option of following this equation. And this is based upon table RCB 9132 design tables, and that's how you can determine your thickness. And basically, small b is the plate dimension, and expressed in terms of inches or millimeters. Q is the maximum pressure drop across the baffle, expressed in PSI or kPa. B is a table value that's shown in table RCB 9132, and linear interpolation may be used for that table. That's the note. And S is the code allowable stresses. So the next thing is for fillet welds. We want to weld the formula is you have to do both sides, and the weld thickness has to be 3/4 of the thickness minimum. For Class C, for leaf seals, there's a distinction made between materials. So they say use equal or greater than a 1/4 inch for carbon steel, and for alloys they allow you to use 1/8 of an inch. For welded in materials, they say just follow the same rules as Class R. For fillet welds, they say follow Class R. And for Class B, just follow the same rules as Class B. RCB 5 floating end construction, in particular 5.1 internal floating heads types S and T, there's distinctions made between Class R units and Class B units. For example, for a single class floating head, which I'll abbreviate on our notes here as FH, the inside diameter of the nozzle center line must be greater than a third of the inside diameter of the nozzle. Now, that's the same for Class C, is the same for Class R, and then for single pass floating heads, it's the same for R as well. Now let's go on to the multi-pass floating heads. What they say is the minimum crossover area for flow between passes must be greater than 1.3 the times the flow area through the tubes of one pass. In comparison, type C says use 1.0 rather than 1.3, and for type B you use the rules of Class C. Part 5, if we go down and have a look at 5.3, what we can see is that has to do with externally sealed floating head tube sheets. In particular, they point out to type W, and in particular 5.31, which is lantern ring construction. So in this case, you need to use a square braided packing. If you're using that, it's for the applications for water, steam, air, lubricating oil, or equivalent. And it must be used in applications equal or less than 375 Fahrenheit. And you need to refer to table RB531, which is some information about the dimensions, the maximum pressure for an externally sealed floating head tube sheets. And it basically has the nominal shell inside diameter and the maximum design pressure. Now the next one is the Class C, and they basically say using it for water, steam, air, lubricating oil, or equivalent. And then it says joint design and packing. You can use it, but the temperature must be less than 600 psig. And when you look at Class B, they're saying go and use the rules of Class R.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.